Hello and welcome to another video. In this video, I'm going to be exploring the new Nanite technology that is part of the new Unreal Engine 5 early access. This is only going to be a very high level overview of the technology. I'm not looking to go into deep explanation under the hood of what's going on. Epic have already done a video about that, and I really encourage you to look at that because there's really lots of really good information in it. But if you're still looking at that video and some of the documentation and some of the other videos that people have begun to put out, and you're still scratching your head a little bit and going, I still don't quite get what's going on here, well, I'm hoping that this is going to be the video for you. So I guess the best and first starting point is by asking the question, what is Nanite? Well, Nanite is just a new mesh rendering technology in Unreal Engine 5. That's it. That's all it is in a simple sentence. Now, I say it's just a mesh rendering technology. I've glossed over an awful lot there. It's a very impressive mesh rendering technology, which Epic say you no longer have to worry about retopologizing meshes. You can use the high resolution source asset from a sculpting package or from a LiDAR scan or photogrammetry data and just bring that into Unreal and use it natively in your scene's environment. And you'll be able to not only bring those assets in, but then also have multiple instances of those assets in your scene without losing any of the quality, and it will automatically do the LODs for you, and you won't have to worry about doing normal maps and things like that. Now, you might be thinking, hey, that almost sounds a little bit too good to be true. And if you explore this level, which is part of the Valley of the Ancients demo, which you can download as part of the early access, you'll look around here and you'll start moving around and you'll say, oh, okay, fine, that's landscaping. And this is probably really low geometry here in the background. And you see, if I spin the camera around, I can see, look, there's half of an asset there. And there's some simple meshes here. So hang on a minute, Epic are just cheating a little bit. And really, they're still pulling the same tricks that we're all doing right now to get our stuff into a landscape. Well, actually, no, they're not. If you really go into this in a lot more detail, if you look at the ground, for example, and bearing in mind, I'm looking at this from a very high level viewpoint. All this environment is made up of meshes. There's no landscape here in the traditional Unreal sense, and when you start to look at that, you begin to think, wow, this is brilliant, but also crazy, because you would never build in an environment like this. It goes against kind of the logic which people have accumulated to this point. And when you start going in here and look at the level of detail, you're seeing, even on my machine where I've just scaled down the settings a little bit to cope with the performance, you really begin to see some of the granular details here, and it's very impressive. And you're thinking, well, this is really delivering what I want. And again, you can go even further right down to the ground level, and you've got lots of rocks and dust and gravel here, and it's all mesh data. There's no normal maps or clever displacement maps going on here. So how's it doing this? What kind of voodoo magic secret system is going on here that enables this to actually happen? Well, underneath, Nanite is based upon a number of principles that have been around in the industry for a while now and have already been explored by some other companies, especially in the game sector. Now, a good example of that is this presentation from the real-time rendering track in SIGGRAPH 2015. And this is from two developers at Ubisoft. They did this presentation about GPU-driven rendering in games pipelines. And the idea was, and the basis of this was, that for something like Assassin's Creed, how do you display massive amounts of geometry in your game environments? So you need a vast level to populate your scene with architecture. You then got to have also interiors supported with that as well. And then also, how do you manage that with all the other requirements of games in terms of characters, animations, textures, effects, playability as well? How do you do that? Well, they spoke about a system that they used for Assassin's Creed. And some of the basic principles here has already been developed by other companies since 2015, and certainly underpins the basis of Nanite. And that's not taking anything away from the developers at Epic. They've done an incredible job, but it seems very interesting to see how this has developed over time, and now Epic are in a position where they can now start putting this out into the Unreal Engine for people to now start utilizing. Okay, so what I'm now going to try and do is I'm going to attempt to explain how Nanite works, what it's doing with your data, and how is it different to how you might be working right now. Okay, so the first area we're going to look at is getting your data into Unreal 5 and enabling it for Nanite. Now, the first thing to realize is that it's no different to how you currently work. There's no special process that you have to do. You don't have to set up your meshes in any other way than what you're already doing. And this is really something that Epic have been very keen to emphasize, in that they're not looking to radically overhaul the current asset creation pipeline. They say that how you work right now and creating meshes should be exactly the same. A Nanite mesh is basically the same data that you've always worked with. You still have to have a material on it. It still supports UVs, vertex colors, all that kind of stuff. Essentially, just keep on working in the same way you're doing right now. And once you bring in your data through the usual methods, it's very easy to enable it for Nanite. The first and most obvious way of getting data in is continue to use Megascans. In Unreal 5 now, Quixel Bridge is integrated through the viewport, so we can actually access it from directly within the engine, which is really good. Now, this is the data set I've got here, and now there's actually together with the usual low, medium and high quality settings, you now have an option for Nanite. And then so when you download this and import it in, it will automatically be Nanite enabled, and that's it. You don't need to do anything. Now you can see that as well from within the UI. If I select this this mesh now and find it in the content browser, if you just hover over it and you get the pop-up appear, there'll be in amongst this big list, it will say Nanite enabled true. Let's say, just for this example, that this mesh already existed in your level and you've migrated it over from Unreal 4, but it's not Nanite enabled. How do you then enable it for Nanite? Well, again, that's even simpler. You can literally just right click the asset from within the content browser, go to the top of the menu here where it's got the static mesh actions, and then just choose enable. You can also disable something here as well. You've got the choice of both options. The other option is to literally just double click the asset and go into your asset editor, and again in the panel on the right hand side you've got an option that says Nanite settings and it's got enabled. Just turn the box on and that's it, you're good to go. Now finally, the other option is when you actually import data into Unreal. And to do that, it's just you follow the same old process. You can right click into the content browser, go to import asset, choose an FBX that you want, and when you load it, there'll be an option here at the very top to choose build Nanite. And when you do that, it will enable the object or mesh to be rendered with Nanite. And that's it. That's really all you have to do. If nothing's changing and you're not doing anything special to the data to prepare it for Nanite, then what is Nanite doing behind the scenes? What type of things is it doing to your data in order to basically work its magic? Now, once we have data in Unreal, we can visualize it. And to do that, you use the Nanite visualization modes. They're available here, and you've got a number of different options here, but we're going to choose triangles. Now, this will display the mesh and display all the triangles that make up this static mesh. And you'll notice this weird outline. Well, this is the color calibrator mesh, and this is the material preview mesh. And the reason why they're not rendered the same way is because they're not Nanite enabled. So we can see straight away using this draw mode exactly what's Nanite enabled and what isn't. And if we go really in close to our objects, these are the original triangles that make up the mesh, because when you start zooming away, you'll begin to notice the triangles are starting to now change. Some will draw over here and get larger. This is what Nanite is doing. It's doing some weird swapping of the triangles. But the original triangles are what you see when you get really close to the mesh. And we can see those in the original source asset that we can actually download from Bridge. I've got Bridge loaded up, the standalone version. This is the mesh that I've actually used as part of my scene. And these are the LODs and everything that I've downloaded. And then I've actually got that into Maya, so we can take a look at it. So this is the source asset from Megascans. Now, when we look at this, the first thing I noticed was that, well, just wait a moment. The topology here looks different to what is actually viewed in Unreal, because I can see here, this isn't the same as what I'm actually seeing in Unreal like this. We can see here that there's all these triangles are more or less the same size, and they're just more or less uniform across the entire mesh. This isn't the same mesh data. What's going on here? Well, then I realized the reason for that is because this is not the original source asset. This is an LOD 0 of the source asset. And the reason for that is because you don't always download that from Quixel's Megascans. If you go over to Bridge, in the list you've got, you can download the FBX file and you've got a list here of LODs. In the extras section here, you've got an option that says high poly source. And this is often turned off by default. So when you turn this on, not only will you download all the LODs of your choosing, but it will also download the original high poly source mesh that these LODs are generated from. And now that we have this in our scene, we can zoom right in. This is the original high-res source asset that Nanite is using. So this is the asset that actually gets imported into Unreal when it's Nanite enabled. It doesn't bring in the LODs, it just brings in this original high source asset. And that would correlate because with the Quixel Bridge Unreal 5 integration, which is this version, we can see this is what the Nanite option is and why it's different to the low, medium and high quality. If you choose any one of these, you're actually just going to bring in the LODs, the LOD version, which is only going to be some like 20, 30,000 triangles. What you really want, and to maximize Nanite, is to use this version of the mesh, because according to Epic, they say specifically a good candidate for Nanite is any mesh data that's got lots of triangles, and also triangles that are going to be very small on screen. And I think this is pretty much a very good representation of what they're actually referring to. Also, this mesh could have multiple instances in the scene that you want to work in. And also, it's more than likely that this is actually going to act as an occluder for other parts of your environment as well. So this mesh, ticks every single one of those criteria. Now, what we can determine from this, if you use Megascans, it's going to ignore the LODs and just bring in this really high resolution source asset. When it comes to creating your own asset, then you can essentially do the same. You don't have to worry about doing the LODs and generating all the things like the normal maps. You can just create a really high resolution source asset. Don't necessarily worry about the topology, because if you look at this asset, the topology is not exactly that neat and tidy, but it's very conducive when you work with scan data, be it photogrammetry or point cloud that's been converted to a mesh. This mesh, even with this number of triangles, which is something like over 400,000, this still has a very simple UV map. Now, this is by no means the neatest UV layout that you'll see, but it works. And this is essentially all you really need. So long as there's a UV set on the mesh and it has a material and a texture, then you're good to go. Okay, so we now have an understanding of the type of quality of mesh that Nanite needs to really work its magic. What's it doing? If we know that we don't have to worry about creating LODs and retopologizing the mesh, what is Nanite doing? Is it doing it for us? Is it swapping it out? Is it doing some kind of special conversion? Well, what it's actually doing is it analyzes the mesh when it imports it into Unreal, and it analyzes the triangles of that mesh and then puts those triangles into a number of groups. And those groups are called clusters. Epic are saying that they try and maintain a threshold of a maximum of 128 triangles in a cluster. Now, why does it need to do it? Why create the groups? Well, by creating the groups, it's essentially breaking apart the mesh. It's separating the triangles into groups that it can control. And once it does that, it's able to swap those groups of triangles out for varying levels of detail based on, say, the camera view. And we can see that in action when we change the visualization mode to clusters. So these are the clusters right now in this view. Now, when I get really close, the clusters are all changing. They tend to be getting smaller and smaller because we need more triangles on screen, because we're up close to the object and we want to see a highly detailed object in our viewport to maintain that quality. When we move further away, the clusters start to change, and as a whole they start to get larger and larger until you're further away and you can really start to see quite some big clumps of clusters. This is basically triangles being swapped out. But what's interesting is that if you move the camera around, not all the clusters change. Some of them stay the same. It just really depends on where the camera is, what it's looking at, what Nanite needs to do in order to maintain the quality on screen. And essentially this works in the basic same principle of a traditional LOD. Your highest level of LOD will have smaller and more triangles in its mesh, and then when you zoom away and you're going through levels of detail, and when you're really far away, you're going to have fewer triangles as part of your mesh, and those triangles are generally going to be larger. So it's the same basic principle, except it's triangle based LOD. Each cluster, essentially think of it as each cluster as its own LOD, and then when it camera moves and it swaps it out, it replaces it with a different LOD of clusters. Okay, so what's the advantages and benefits to using these clusters? Why do they make a difference, and why are they better? Well, it really makes a difference when you look at the methods that Unreal uses to optimize your scene and decide what gets rendered and how it's able to maintain a frame rate. One of the methods it uses, and perhaps one of the most common methods, is culling. So in other words, it only renders what it needs to and then just culls anything else. And it uses two basic criteria: camera frustum, the field of view, and occlusion. And Nanite is no different, and Nanite uses both of these criteria when it's deciding what to render in your scene. But the clusters give it far more control in deciding exactly what gets rendered. Now, to best describe this, let's look at the idea of camera frustum first. This is our camera. This is what it's looking at, the view here. I've got it pinned in my viewport. And as you can see, it's looking directly at this object here, and it's taking up most of the field of view. Now, what I've done here, I've duplicated the object multiple times, very crudely, I admit, but this is just meant to represent a large environment with lots of objects of many triangles. Now we can see from the field of view here that this foreground object is taking up most of the field of view, but also this object here is actually also falling within the camera's frustum, as is this object over here. Now, in the traditional sense of culling, it works like this, and this is all explained in the documentation. So this is coming directly from Unreal's website. So in this diagram here, the field of view for the camera, the frustum, is represented by this yellow triangle, and these white objects are a part of our scene. Anything that falls outside of this yellow triangle gets culled. So with this slider, we can see that all these red objects get culled. What happens when you've got objects like these? So this sphere and this cube here, part of it falls outside the field of view, part of it is inside the field of view. So what happens then? Unreal has got no option but to render the object, because the culling is based on, it's on a per object, per actor basis. So even though part of it falls outside the camera's field of view, it's got no choice but to render it. If it culls it, it's just not going to be rendered at all, and that could look really odd. Now, the only method of mitigation to this is to use a lower level of LOD, and that makes perfect sense. So, but that might not be possible, because what do you then do if the camera is very close to the object? And we can simulate that by taking the camera here, and if I zoom in really close, I've got no choice now. My object is taking up all my field of view. My camera is very close to the object, so I need to make sure it's a higher level of LOD, so that way it will always look very high quality on screen. But of course, what I'm having to do, I'm having to render the entire object, because I can't cull part of it. I can only cull all of it. Well, this is where Nanite comes in. What Nanite is able to do, and say, well, actually, I work on a cluster basis. So I'm able to take my mesh, which I've already analyzed, I've already created my clusters, and of course, I've already swapped out my clusters based upon the camera distance from the object. And now I can decide and say, well, actually, I'm able to determine that if I just get to zoom in here a little bit, I can then say, well, actually, if I look at these clusters now, some of these ones fall outside the camera field of view, as do some of these ones down the bottom here. So you know what? Cull them. So you're culling clusters, you're not culling the entire object. And this is where Nanite really starts to provide a significant advantage. It's able to maintain a high quality visual in your viewport, but also it's very optimal in the way it does it. It's only rendering what it needs to. It's not having to render the entire mesh. And remember, this mesh is very high. It was over 400,000 triangles. So that's very high, even for current technology. So it's not working with LODs. It doesn't need to. So what it's doing is it's just eliminating or culling the clusters it doesn't need. Same thing as well is if you start to pull the camera back a little bit and more objects come into its field of view. If you take camera a little bit and say you move it off to one side, so now you've got more of this object here in the background being seen. Again, part of it is actually inside the field of view, part of it is outside the field of view. So therefore, what Nanite is doing is saying, well, I'm only going to render the clusters that are visible to the camera and fall within inside the field of view. So that's the first method of culling, its criteria. Now the next level is based on occlusion. And again, with this example, we can see, as well as part of the object falling outside the field of view, part of the object is also being occluded by this object. Now again, the same basic underlying methods are the same. Because the culling in its normal form is based on per object, per actor, Again, it's the same basic principle. It's got no choice but to render this object in its entirety. Unreal can't decide what it's able to basically occlude. So this object here, for example, we can see in the diagram, it's occluding this sphere and this one and probably this one, or it's occluding part of it. But because it can't cull it on a per cluster basis, it's having to render all of it. And again, the only mitigation you've got is level of detail. But again, what Nanite can do, Nanite can say, well, actually, I'm able to analyze this again and say, well, okay, I can now determine that if I look at my object here, based upon this camera view, these clusters here on this right side of the mesh, they can be occluded. They can be culled because they're not inside the field of view. These ones here, though, they are inside the field of view, but actually they're being occluded by this object here. So therefore, you know what? You can cull those as well. And therefore, I'm only displaying and rendering in high detail part of this middle bit here. And again, with this object here, this object also is probably within view, but we can't see it because it's been included by this object here. And again, if you take the camera and start to move it even further, you can start to then see how it really starts to make a difference when you move it to one side. And now with this view, we can see I've got this object in view, and now this object is starting to be occluded, but then this object back here is just about visible. And then you've got also another object, probably this one here, there it is just about in view. But again, if this was traditional object-based culling, this object would still be being rendered in its entirety, just a lower level of detail. But what Nanite is able to do, because it doesn't work with LODs, it just works in clusters, it's say, well, I'm only going to render the clusters that are visible and the clusters that aren't being occluded. And that's how it's able to essentially always maintain a very high level of detail in these objects. If I look around here, I'm moving the camera around and I can't see any change in this mesh at all. Even if I was to lower the actual camera speed and move very slowly, what you'd expect to see here is the LODs start to move around, or maybe a slight pop in the texture map and also the mesh, but you just don't see any of it. And I know it's actually happening because if we just go back to our visualization modes, I know that the swapping is going on because we can see it. Look, there's so much swapping going on here, even in the ones back here as well. So again, if you look over here, we can see that these are also swapping in and out at the same time in anything that's actually being displayed on screen, but you just don't see it. It's just not visible. And that's something, again, which is another significant advantage over using LODs. If I was to pop over into Maya again and look at my mesh and say, well, look, this is my LOD group, and again, when I start moving in and out, for example, you'll begin to see the things will start to pop and change. So like there, see? Now you can mitigate this by ensuring you've got good solid topology, making sure your edge loops are really lined up. You've got good texture mapping, good UV layout, good normal mapping as well. All these things make a difference, but they take time and they require more work. And you can do it really well, so you can minimize the amount of popping. But the problem is, once you start getting to a certain distance away, this level of detail is quite low. It's only just over 1,000 triangles. But when you get into the more closer, this one's here at 32,000. And again, this is a very extreme example and perhaps not representative of what you see in some game engines. And the LOD creation and generation and optimization in Unreal is very, very good. You don't always spot these joins. However, you still have to give it good data to work with. And you still have to have a good mesh, which is well textured and got good topology. But with Nanite, you don't have to worry about that. It's doing it for you, which is how it's able to maintain this high level of detail. Even if you look around here, even at this level of distance here, this distance from the camera, this would probably be quite a low LOD with a normal map, which is fine. But when you start moving around, you can begin to see that this is not a normal map, it's actually a mesh. And again, that's something that Nanite it just gives you a far better visual fidelity for your assets. But also, where it's also making the savings is its memory usage, because Remember, for LODs, you need texture maps and normal maps, and they can significantly add to your memory usage as well, which is another topic we're going to be looking at. But as you can see, it really does make a big difference. Having this cluster-based approach means that Nanite can really break apart and segment parts of the mesh and only render exactly and precisely what it needs to and maintain a high visual quality at the same time. That's how Nanite is working. I think I've got it right. I hope I've got it right. And I hope I've been able to explain it to you in a very simplistic way that you can understand. Okay, so knowing what we know now about Nanite, and hopefully if my explanation is correct and been understood, we can now revisit the Valley of the Ancient, and we can perhaps have a look at what is going on in this particular environment. And I think what's very telling is that when you turn on the overdraw for this environment, you can really see just how much is going on, where Nanite is essentially trying to draw multiple meshes, objects and triangles, and they're all overlapping at any one time. And again, the heat map is just going absolutely crazy because the ground is made up of multiple meshes. It's not a landscape, and apparently landscapes in Unreal are not supported by Nanite at the moment, so maybe that will change in the future perhaps. And again, if you look here, you can even see again the outlines of the meshes and the amount of overlap that's going on. And if you go back to normal mode and actually just dip below the surface slightly, you can see that there's all this data going on below the surface which you don't see, and there's a lot there. I mean, I don't know what this object here is. That's absolutely huge. And again, it just kind of goes against the logic that you've perhaps been used to working with when it comes to building real-time environments. So you wouldn't do that. You just wouldn't have that wastage. But I guess this is how the guys put the level together. But I think it's been very interesting, the fact of being able to do it, and also Nanite has just been able to cull that data and just go, well, if I can't see it, I'm just basically going to ignore it, really. So Epic are kind of true what they say when they say, well, you don't have to worry now about retopologizing your high-res source asset. You can literally bring it in and let Nanite do all the hard work and heavy lifting for you. And by the way, you don't need to worry about baking out that normal map anymore. We're just going to be working with the raw triangles, and again, you'll get a very, very high quality asset. What I do think is very interesting though is that even though this amazing things, it's all too easy to fall into a trap of just going, okay, let's just throw everything at Nanite and everything's going to be like a silver bullet. And I don't think that's actually true either, really, because I think even Epic have admitted, although there's lots of advantages to using Nanite, as we can see, there are still some practical limits that you have to be aware of. For example, the number of instances in your scene, and how many do you want to have? How many triangles are there to that mesh and instance that you're trying to render? Also, you still have to think about materials and the material complexity, and then also the output resolution that you're trying to render to, be it a real-time game or whether or not you're doing any kind of rendered frames. These are all things you have to consider. Plus, you've got the combination of hardware and software as well. And I think it says that due to the nature of Nanite streaming mesh data from disk, then it recommends that solid state drives should be used as a runtime storage. So again, these are all things that you have to consider when starting to use this technology. So an area which I haven't touched upon is materials, and I think it's just worth discussing this now because it's still something that you have to consider. But in the recent stream from Epic where they presented Nanite, they spoke about what they were doing. So I'm not going to go into all the technical details, so I'm going to keep this really as simple as possible. Any real-time technology such as Unreal Engine uses something called drawcalls, and a draw call is basically essentially it's telling the GPU, CPU what to render and how to render it, and it uses a draw call to do that. And a draw call in the most basic term is a group of polygons or triangles that share the same properties. In Unreal language, that means a group of polygons that share the same material. The way Unreal works is that it does a draw call for every material that's used on a single mesh. So for example, if you've got a tree and there's a material for the main trunk of the tree, that's one draw call. If you've then got leaves on that tree, as geometry, and that's got a texture material on it, that's another draw call. And then if you've got the tree has got some other branches which have got another type of material on it, that's a third draw call. An object could have anything up to 3, 4, 5, 6 draw calls, depending on how many materials it has assigned to it. In the stream, they mention about the draw calls, and what they're doing from a geometry point of view, they're loading the entire scene into GPU memory and doing one draw call across all the geometry. What they're also doing from the material point of view, and again, if I have understood this correctly, they're doing a slightly different pass on it. So now what they're doing is they're doing one draw call for the material, but only if it's present in the scene. They're not doing it on the per object basis. And I guess what that basically means here is if we look at this scene here, for example, closely, we've got this rock here, and we've got this this foliage here. This, say for argument's sake, they're both using similar materials, or they're both using the same materials. And let's just say, for example, they're using 3 materials. Now, the way Unreal works is that it would do 3 draw calls for this object, and then 3 draw calls for this object. What they're now doing is, instead of doing that per object, they're saying, well, hang on a minute, there's 3 materials being used on both these objects. We're not going to do 6 draw calls now. We're just going to use 3 draw calls, 1 per material. And no matter where that's used in the scene, it could be used over here or over there, over there. We're just going to do it across the entire scene. Now, that is a massive saving. And that's a very different paradigm to how Unreal works right now. And I think that's specifically related to Nanite. I think. I could be wrong, but that's what my interpretation of that. And if that's true, and I've got that right, that's massive, making massive savings on the amount of draw calls that having to be sent to the GPU in order to determine what's being used. And again, that makes a massive difference if you've got multiple instances of the same object in your scene. Because if this rock is duplicated, say 10 times, and it's got 3, and it's doing 3 draw calls per object, it's doing over 30 draw calls. If you're now just doing 3 because there's 3 times the material in the scene, that makes a massive difference, and also a significant saving and optimization. So that's really quite interesting. Also, what comes into play is where Epic say about you should enable Nanite on any type of static mesh, because it's going to be making a saving in some way, shape or form. It might not be able to cull things, but it might be able to lower the memory footprint. And again, if it's changing the way it does the draw calls for the materials, then even older meshes are going to benefit from that in some way, shape or form. Now, to best explain maybe about how Nanite can actually benefit other types of data, I took this bistro scene and I imported it into Unreal, and I converted everything over to use Nanite. Now remember how we know how Nanite works with the triangles, but of course with this data it's already been very heavily retopologized, so there's just not the level of triangles that we would get from a scanned mesh from Quixel Megascans. So really there's only a limited amount of triangles here to work with. So Nanite in some ways can't really break things apart in the same way in order to create its level of detail. Let's just take a look about what you can do with it. So here we are in Unreal 5. So this is the same asset now in our scene, and this is all Nanite enabled. So if we were to turn on the visualization modes now, let's start looking at the triangles. So these are all the triangles in the scene. So of course this is pretty much raw as it's come in. Now of course if we zoom out, there's not really too much change going on here because there's not too many clusters. Except maybe down on the ground. And if we look at the ground inside Maya, you can see that the topology looks very, very different. Essentially, there's just more triangles to essentially work with, or for Nanite to work with. Same as on the ground. I mean, they're fairly uniform, but there's certainly more triangles that Nanite can go to work with, and in order to create its clusters. Now, if we start looking at those clusters, if we zoom in, they'll change on the road because there's more triangles to work with. But of course, when you start zooming out, they'll start to get bigger. But of course, nothing really changes here. You get some very odd shapes here that's going on. But Nanite is still trying to work its magic. It's still trying to do LOD. And you can see there there just isn't that much change going on that we would normally expect. But then again, the geometry is still fairly lean anyway. It's a fraction of what the Megascans asset was. But of course, you're still going to get some benefit here when you've got curved surfaces, and that's where you're likely to have a higher polygon and triangle count because you want to maintain curvature in the soft edges. Now, of course, even though it may not be benefiting too much from some of the LOD stuff, you're still going to reap some of the rewards of Nanite when it comes to culling, for example. Now, if we look at the overdraw, this is where things do get a little bit more interesting because, again, look at the heat map. And again, this is where, remember, Nanite is trying to draw multiple objects on screen and objects that are in front of each other or maybe close to each other, particularly with overlapping geometry. And of course, you notice that here on these curbstones because, of course, again, these are overlapping meshes, so it's not really being built very efficiently. But again, we're still getting some benefit by using Nanite for this. And again, if you look at the heat map, this is when we've got a lot of overlapping surfaces here. And you can then, for the clean lines, you can really begin to see the benefit here. And if you look at these meshes here, it's kind of crazy in some ways because you wouldn't necessarily build it like that out of choice. Let's just see if we can find the asset now inside the actual scene itself. So we've got these objects here. So again, you can see they're not actually dotted up, they're actually overlapping. And again, if we go to the wireframe mode, you can see there's actually solid blocks of polygons there. So again, it's not a very efficient model at all in the way it's been built. However, due to Nanite, we can still use Nanite to benefit from that, and we benefit in terms of the overdraw and the culling. So even though we're not getting too much culling in terms of things like clusters, for example, or triangles, Nanite is still able to hopefully cull some of these objects that are out of view via the occlusion method because they're occluded from view. So in some ways, there is still some benefit, even on a mesh like this, which has been heavily optimized already, to enable Nanite and just let it do its thing, really. Also, as well, and it comes down to the materials. And again, if I have it correct in terms of the number of draw calls, again, you're going to be saving a significant amount of time with these objects because this stone texture, for example, is used on every single building. So you're having to do a draw call for each material per object. But if you're only doing it once in the entire scene, you're really going to save yourself a lot of time and effort, and also save yourself a lot of optimization in terms of these buildings where you've got a lot of intricate surfaces. So again, there's some interesting benefits there, I think, to be looked at in terms of using Nanite. And I think that's what Epic are trying to allude to, is sort of say, well, actually, you know what? Just because this isn't made up of loads of triangles and it's not come from any kind of source like photogrammetry, still basically enable Nanite, because even though you might not be benefiting from some of the triangle count stuff, you're still going to benefit from the memory usage and some of the culling, for example. Now, one thing I did notice as well in this level, and the same as in the Valley of the Ancient, and I don't know if this is maybe a Nanite thing, or maybe it's a Lumen thing, or maybe it's both, but I noticed I was getting a lot of light leakage. So, for example, this is why I added this object here, this cube. So if I turn this off and we just go to the other side, we can see you get this weird kind of light coming through these windows here. Now, of course, this is meant to be a solid wall and a solid mesh, but of course, this looks really odd. I mean, I actually like the light streaming down onto the street like that, but of course, it doesn't work because the building's meant to be blocking that out. And so what I did is I just added this cube here as a kind of light blocker. And that's the same for what's inside in the Valley of the Ancient demos as well. So I don't know if that's maybe a Lumen thing or whether or not it's a Nanite thing, but I've noticed that's happened a few times. And I've also had to do that as well on the other environment. I also did on this level, for example. This is why I added this odd plane here. Again, if I was to move this out the way, I get this weird light streaming down onto the mesh. And I tried a lot to try and get rid of it. And there's nothing I could have. I thought maybe it was the intersecting of the meshes maybe, or was it maybe the quality of the rendering? So I changed my settings as well, but there's nothing. And so then what I did is just went back to an old school method, which again is very common in games and has been like this for a long time, is you just put like a blocker in there, because I guess when you're rendering, any type of crack in the surface in some way, or missing edge or face in the topology, means that the light's going to come through. So then when I move this over, that disappeared. So it's interesting that even though we've got this amazing technology, and it is amazing, there's no denying that, you still sometimes got to use a bit of an old school method in order to basically get this to work. Actually, I just need to move that over a bit more. And again, if you look in the Valley of the Ancient demo, you'll see these light blockers all over the place. And I don't know if it's maybe the mesh and there's not enough, because there's no back face to this as well. Maybe if it was a bit more closed off, or maybe is it just down to topology? I don't really know, but perhaps maybe Epic might elaborate on that later on in another stream. So anyway, so that comes to the end of this video. This is so I hope this has been useful to you. I hope I've been able to explain Nanite in a very basic way, and that you maybe have a better understanding of it that you otherwise didn't have before. And I hope that I've got my interpretation of it right, but I think I've got it more or less right. But of course, I'm happy to be corrected on that. But anyway, thanks for watching this video, and I'll see you again next time.